Okay, so to jump back into the lecture, last time we were looking at this example. We have talked about nodal analysis. So hopefully by now everybody has a good idea of at least what nodal analysis means, what it implies, how that's a different version, a different way of approaching the problems than maybe we've talked about in the past. It's a linear, algebraic approach. We define the circuit as a system of equations that we represent then as matrices, and then we use matrix algebra, linear algebra in order to solve. What we saw was that for nodal analysis, the base case is independent current sources only. That's sort of like the starting point. We have independent sources and we have resistors. When we have independent sources and we have resistors, those two types only, then we can perform the analysis using or what we call by inspection, right? Which means that we can generate the current vector, the I vector, as well as the admittance matrix just by looking at the circuit. Real quick, right? The current vector is easy to generate. It's simply just going to be, if you consider the rows to be the node numbers, right? 1, 2, 3, 4, 5, 6, whatever, then each element of the current vector is just the independent current source or the independent current flowing into that node, right? So you look at all the different nodes. If it has an independent current source attached to it, then you put in the value of whatever current is flowing into the node. If there is no independent current source attached to it, then that would be a 0. The admittance matrix, right, there's two different types of elements in the admittance matrix. There's the diagonals, and then there's the off diagonals, right? The diagonals, if we keep all of our signs consistent with what we did in the example, the diagonal elements are positive, and they represent a sum of the admittances, all the admittances connected to that node. Remember, admittance is 1 over resistance. So we've been representing it as the sum of 1 over R IK, and then you just look at all the adjacent resistors. So you do that going along the diagonal. Along the off diagonal, the values are negative. And 99% of the time, again, assuming there's not more than one branch, parallel branch that spans between the two nodes, you put 1 over the spanning resistance. So if we're talking about a matrix and we're talking about element 1, 4, then what you would do is look for the resistance that connects node 1 and node 4 and minus 1 over that resistance. If there is no resistance that connects the two nodes, they're not connected, then you would have minus 1 over infinity, because that's an infinite resistance between the two nodes, and so that ends up giving you a 0, which means that element is gone. The voltage array is unknown, so those will just be populated by the variables. When we have a dependent source, what we see is that it changes the problem a little bit. It messes up our ability to use inspection. And what it specifically does, at least in this case, is it breaks the symmetry of the admittance matrix and changes this element that's connected to node number 1. So what we did was, in order to solve this type of problem, we went back to what we had done originally, which was writing out the KCL equations and grouping them by the variables, the voltages, and then putting it into a matrix form, and then that essentially gives us everything that we need in order to solve. So where did we stop? Essentially, I mean, really, since we don't have numbers, this is essentially the end of the problem, right? Step 8 would just be, if we had numbers, and we will do some of these with numbers, solve for the voltage array by inverting y. So I don't know if we really need to write it out, but I will be equal to that. Okay. So that's the second type of problem that we could potentially see. Now there's two other types of problems that we haven't discussed yet. We haven't discussed what happens when you have any voltage sources in the nodal analysis, and we haven't discussed what happens when you have, either dependent or independent voltage sources in the nodal analysis. Okay, so the next section, we're going to talk about nodal analysis with voltage sources. And so, good news. This actually will make the problem easier to solve as opposed to making it harder to solve. I'll put that in quotes because sometimes things that are easier can have quirky aspects to them, but overall easier to solve. And so let me ask you, why do you think an independent, let's just focus on independent, an independent voltage source would make these problems easier to solve? Take a look at this back here. So what is it that we're solving for, right? In nodal analysis, generally, right, we know, yep. Right. Bingo, right? If I were to replace this, or let's say, this with an independent voltage source, I don't need to solve for V1 anymore. That's known already. So then I can just go ahead and cut that out of the nodal analysis. So I'll eliminate the first row of the whole thing, and I'll eliminate the first column of the admittance matrix, which in this case would reduce the n equals, the 2 by 2 problem down to a 1 by 1. So you just have to generate a single equation in order to solve. So that's what we're going to show here. So really all you have to know is just how to appropriately eliminate the variables or eliminate parts of the expression from the problem definition or from the way that you're describing the problem. You don't want to accidentally remove variables or parts that are needed, and you don't want to accidentally leave something that doesn't need to be there. So we'll do, like we've done several other times, let's use an example in order to demonstrate. And so this is going to be nodal analysis. Now the one thing here I hope that everybody is sort of realizing is even though we're doing different types of nodal analysis, the method is not changing that much from example to example. So it's sort of a twofold. We're exposing you to other types of nodal analysis problems. At the same time, we're also giving you lots of practice. So this is intentionally repetition, different types of circuit topologies. Either we're using the by inspection method or we're going to write out the equations. Now, so 9, 12, 12. And for this one, we are going to actually come up with a numerical answer. 6 volts, 12 volts. First thing, let's label everything. The main thing is just labeling the nodes. Okay, so this is going to be node number 1, node number 2, node number 3, and node number 4. There's no parallel branches, so we don't have to define any other currents. For example, I know that this will be I13. I know that this will be I42. I know that this is equal to voltage 34. So we can just refer to everything by the double subscript notation. In previous problems, we had said that we're just going to pick a reference node and that we really hadn't given that much thought to any strategy for choosing it. In a problem where you have voltage sources, there is definitely a strategy, which is not very difficult, but there's ways that you can make the problem easier or harder depending on where you choose the reference. So let's say, for example, I were to choose this as the reference right here, node number 2, which doesn't seem like a logical choice, but then that means that the voltages we would actually be solving for we would call it V1, which is really V12, V3, which is really V32, because right, V1 minus V2, this equals 0. V3 minus V2, this equals 0. And V4, which equals V4 minus V42, which is V4 minus V2. Again, that goes away. Are any of those voltages known? No. There is no voltage source between 1 and 2. There's no voltage source between 3 and 2. And there's no voltage source between 4 and 2. So the voltage sources will help us, but not as much as they can. Ideally, what we would want is to set up our reference such that we can just scratch 2 of those equations off altogether. And what that means is we would like the reference node to be one end of the voltage source, or as many of the voltage sources as possible. So now if I pick this as the reference node, you notice that our voltages will be V14, V24, and V34, right? And this is known, and this is known right off the bat, because there is a voltage source between 1 and 4, and there's a voltage source between 3 and 4. So when we ask ourselves how We want to choose a reference that's going to be adjacent to as many voltage sources as possible because of what we just said a second ago. Now the reason why I put a third step in here that says to determine the structure of the problem is because we have a way that we're used to seeing this problem. This is going to be a little bit different because we're going to start eliminating variables. When you first start doing this type of problem, it's easier to write it out in the bigger form and then cross out what it is that you do. So let's determine the structure of the problem. First things first, let's set this up the way that we would, quote unquote, normally, right, if there were no voltage sources. There's 4 nodes, so n minus 1 is 3, means that we have a 3 by 3 admittance matrix. We have 3 potential independent current sources coming into the nodes, and we have 3 unknown voltages, V14, V24, V34, which we'll refer to as V1, V2, and V3. Now, these values here should be known. There are no independent current sources in this circuit, so all of these values will be 0. They're all 0. Over here, we have 2 values. Normally, this whole thing is unknown, right? V1, V2, and V3 are all unknown. That's what we're trying to solve for. However, in this case, we have a V1 that's known, and we have a V3 that's known. And so the first and the third equation don't do anything for us, right? They don't serve any purpose. We already know what those are. So that means that we can go ahead and eliminate them from our analysis. And so what we're left with is now a single equation that we have to solve. Yes? It's -6 because it's the direction is inverted upside down. Okay, and so right, what we can do is essentially just write out this one equation that's left over. We have I2, which I put a little IND to state that it should be independent, but I don't really need that, to tell you the truth. And that is going to be equal to Y21 times V1, Y22 times V2, Y23 times V3. Because this is only one equation, we don't have to put it back into a matrix form in order to solve. There could be a case where we go from 3 equations down to 2. In that case, we'll do a homework problem at some point like that. In that case, we would want to go back to a matrix form, but we don't have to do that for this one. So the yellow is what's going to be the equation that we're going to use. So 0 equals Y21, V1, etc., etc., etc. This is known. This is known. This is known, unknown, known, known. Let's talk about the values of the admittance matrix for a second and where they come from. So what is this value right here? Okay, we can use our same, as long as we don't have a dependent source, okay, we can use our same by inspection method for determining y21, y22, and y23. So what is y21 going to be? It's an off diagonal, which means it's going to be negative. It's going to be negative 1 over the resistance between nodes 1 and 2. So let's go up and look at what that is. So between nodes 1 and 2, there's 12 kiloohms. So it'll be negative 1 over 12,000. And that's what we have right here. Okay? Y23, same thing. Between nodes 2 and 3, there's, again, a 12 kilo ohm resistor, so we end up with negative 1 over 12,000. The diagonal element, all right, Y22, that's going to be the sum of 1 over all of the adjacent resistances. So what are those values? Adjacent to node number 2 is the 12, and the 6. So Y22 will be 1 over 12,000 plus 1 over 12,000 plus 1 over 6,000, which is what I've written down here. Oops. What I've written down here. And so it ends up giving us a value of 1 over 3,000. Let me give you guys a second to copy that if you want to keep writing. Mm-hmm.
Is there a reason that you're adding all of those together because it's like the resistance values in series, but then because it's Y22 it's the 1 over R?
So we're just using our by inspection method. If you go back to the notes from here, remember that for diagonal elements, it's the sum from k to n, k equals 1 to n, of 1 over r1. In this case, we're talking about two elements, so it would be 2k. So that's the reason why it's 1 over r21 plus 1 over r22 plus 1 over r21, 1 over r23, 1 over r24. Okay? For the off diagonal elements, it's negative 1 over the resistance that's between them. We don't have more than one path, so we don't have to worry about that parallel the use of the parallel operator. So what we did here was just sub in the values that are known from looking at the circuit, which is this, and we also used by inspection to get this, and this, leaving us only one unknown, which is V2. And then we rearranged things. I highlighted where things went, just using algebra. And what we end up with is that V2 is equal to 1.5 volts. So the full answer is V1 equals 12, V2 equals 1.5, V3 equals negative 6. And that gives you all the voltages of the system. Any questions on that one? Okay. Yeah. So that 0 is just me trying to include that right here. So didn't seem like it was completely.
How come the that equation is 1 over 3,000?
This right here.
Yes.
So if we're solving, we're trying to isolate that value, which means we take this, we move it to the other side, we take this, we move it to the other side, and then we have to divide by the y22. Okay. So now, we've talked about, or at least we've given one example of how to handle independent sources between reference and non-reference nodes. But the fourth out of the 5 cases, remember we said there was 5, independent current sources only, dependent current sources, independent voltage sources between non-reference and reference nodes. This is the 4th one. Independent voltage sources between non-reference nodes. So how do we handle it? What we're going to do is we're going to consider the 2 nodes as one supernode. The name, well, what it means is that we can combine the 2 together for the purposes of nodal analysis and specifically for the purposes of KCL. So remember that KCL, when we defined it, we said that the current flowing into, all the currents flowing into a given node or a given section of the circuit will sum to 0. We haven't used the second variation of the definition. We've mostly just been considering a single node. However, if you look at what's right here, okay, all of these currents should sum to 0. Right. I'll call this IA. No, I don't want to use those letters again. I1, I2, I3, I4. Anything that flows into our supernode should sum to 0. And so that's what we mean when we say supernode. And the reason why this is helpful is because we don't need, like a voltage source between a reference and a non-reference node, we're still going to be eliminating one variable from the analysis. We don't need to solve for VA and VB. We just need to solve for one of them, right? Because if we know VA, we'll know what VB is, and vice versa. If we know what VB is, we'll know what VA is. So what we can do is, because of the supernode, we can put all VBs in terms of VA. We can completely eliminate VB from the problem altogether by simply just saying that VB is equal to VA plus a known value, which is VS. So if we're going to eliminate one unknown, we also need to reduce the number of nodes, or the number of KCL equations, right? It's a one-to-one relationship. So that's how we handle this type. We reduce the number of nodes by 1, taking the supernode and combining 2 together, and we eliminate that unknown using this substitution right here. But anyway, let's go through and do an example which will help us explain how to do it. Okay, so next, apply nodal analysis with independent voltage sources between non-reference nodes. And so what we have is this circuit here. Let me find my stopping point in the notes. And so let's label everything. I labeled the nodes node 1, node 2, and node 3. I did define a couple currents. You can see I called one of these I13 prime, only because there's two paths between node number 1 and node number 3, right? So I don't want to get the 6 milliamp current source mixed up with the current that's flowing along the 6 kilo ohm branch. So I gave it that prime. Obviously, I13 prime is equal to negative I31 prime. We don't have to state that. That's just inherently known. Okay. Next, we know that anytime there's a voltage source between two non-reference nodes, we are going to define a supernode there. So what I'm going to do is I'm going to take everything in the purple and I'm going to start calling that node X, or supernode X. Okay, so now where does that, yes?
Could you just like quickly go over like what non-references is?
Yes, yes. So, and actually we didn't explicitly state that yet. Let me take this and move this down. Right. Every time we do a nodal analysis, going all the way back to, any other example, right, we always have to define what our reference node is. So in this one, what we're going to do we're going to choose node number 3 because that's the way the problem wants us to do it, even though node number 2 makes more sense. Why does node number 2 make more sense? Or node number 1. Either node number 1 or node number 2 make, yes. Bingo. Like we said above, it makes sense to choose the reference node such that it's adjacent, because then we'll be turning it into the easier type of problem. We could do that here. We're not going to do it because that's not the way they want us to do it. But if I were doing this on a quiz or an exam, that would potentially be an easier way to do it. Okay, then now this becomes step number 3, is to define our supernode, which is in the purple. Okay. So now let's get into the nuts and bolts of how we handle our supernode. So this is important. We're going to write out KCL for all the nodes. And I'm going to put a question mark here, all, exactly what that means. Because we will use supernode X, but we won't use the two nodes that are included within it. Okay? So what that means is if we were doing this problem otherwise, okay, we would have to define two KCLs. We would do it for node number 1 and node number 2. We're only going to do one KCL, which is going to be for node number, super node X. So let's go ahead and write that out. So this is KCL for node X. So what we have is 6 milliamps minus 4 milliamps plus I31 prime plus I32 prime. Right? And what we see is that nodes number 1 and number 2 aren't going to disappear from the analysis completely. Okay, we're still going to have to use them, and that's where this substitution right here will come into play. Okay. But other than that, we're using the same process that we've used for a lot of other non-inspection-based nodal analysis problems, right? We're writing out nodal analysis. If you want to go to the most fundamental application or implementation of it, it's you label everything, you define your reference node, then you start writing out the KCL equations for all of the relevant nodes, non-reference nodes. The only difference here is that we are, because of the super node, we're using that instead of nodes 1 and number 2. Okay, the same next step that we would use for any other problem. Substitute for Ohm's law, right? Done that a million times before. So we're left with 2 milliamps is equal to, first I'm going to move everything to the other side. So we have negative I31 prime minus I32 prime. Substitute in for this. What is that going to give us? So how do we substitute for I32 prime? It's going to be equal to some voltage over resistance. What's that voltage going to be? Same subscripts. V32. Well, there's no prime. We never defined a V32 prime. V32 over R. Only reason why I say R23 is because we usually, right, the resistance is the same in either direction, so usually we'll just put the lower number first, and then over here we'll have V31 over R13. This is also equal to V3 minus V2 over R23, V3 minus V1 over R13. And if we look up top, we see that V3 is equal to 0, right? So that goes away. And so if we sort that all out, what we're left with is 2 milliamps is equal to 1 over R23 times, so this, the negatives will cancel out, so we'll end up with times V2 right? And then we'll have plus 1 over R13 times V1. Again, those negatives will cancel out. We know, and so one thing we should probably do when we define the supernode, I'll add this up here. Define supernode and its quote-unquote relationship that's derived from KVL. I'll write that real quickly over here. So what is the relationship? It's just simply an application of KVL, which says that V2 minus V1, actually, sorry, it's the other direction. V1 minus V2 equals 6 volts. Everybody see why that's the case? Right? The voltage going from 1 to 2 is 6. And so if I wanted to do a substitution, I could also say V1 is equal to V2 plus 6. So this can be used for substitutions. Later on. All right, so let's go ahead and, so we substituted for Ohm's law. Well, I'll make it a separate step just for the sake of completeness. Step number 6, substitute for the supernode relationship. And so what that'll leave us with is 2 milliamps equals 1 over R23. So we're gonna replace our V1 using that. So V2 stays. So V2 plus 1 over R13 times V2 plus 6. Right? So we're doing the substitution right there that we pulled from up above. What we'll end up with is the constants on one side. We'll have 2 milliamps minus 6 over R13. I'll pull that piece to the other side. And what that leaves us with is V2 times 1 over R23 plus 1 over R13. And so what we're left with at the end is 1 over R23 plus 1 over R13 times 2 milliamps minus 6 over R13. Anyway, you plug in all the values, which in this case, so R13, what are these values? R13 is 6,000 and then 12,000. So this is 6,000. This is 12,000. It turns out that the parallel combo of this gives you 4,000. This gives you 0.001, and what you're left with is 4 volts. This is another example where, like what we did with the reference and where we had a voltage source between reference and non-reference nodes, it simplifies down to one expression, so you don't end up having to use matrices in order to solve. If we had a bigger circuit, which again, we'll find a good homework problem to address that. If we had a bigger problem and there were two expressions left, then you would still be tasked with trying to put it into a matrix form. And so that's what I was trying to say at the beginning of class when I said that as the problems get more and more complex and as we get into more different types of nodal and mesh analysis problems, it becomes more about taking a look at a circuit and trying to put it into a matrix form. Okay, it's not as straightforward as following a procedure. So you can pick and choose pieces from these procedures. Obviously, if you have a voltage source between two non-reference nodes, you're going to want to pull that supernode piece. That's one tool that you can use. Okay. Let me see where we are here. Can we do this example yet? Okay. Next. So let's ask the question here. What are we going to do with dependent voltage sources? When we have independent voltage sources, we can just get rid of it, right? Let's assume that the dependent voltage source is between the reference and non-reference nodes. So really, not to take back what I said before, there's really 6 types if you want to break it down to each time reference and non-reference nodes. Because there's 2 types of dependent. So when it's a dependent source, we won't be able to simply get rid of V14. We won't be able to simply get rid of V34. What we're going to do is we're going to replace, no longer will we use KCL. Let's say we had a dependent source here. We can't use KCL at node number 1 because we won't know what the current injected by the dependent source is going to be. We can't get rid of it because it's not a known value. So what we're going to do is wherever we have a dependent source connected, we're going to replace that expression. We're going to, instead of using KCL for that node, we're going to use whatever the expression is for the dependent voltage source. That'll give us the expression that we need in order to essentially get full rank for our matrix. Okay, so it'll be essentially a switch. Like we've done a lot of other times, actually let me write that down. So how will we handle dependent voltage sources between reference and non-reference nodes? The simplest answer, use the equation or the description of the dependent source in place of KCL for that node. And this makes sense because we cannot define the current through the voltage source. There is no Ohm's law for a current source. For a current source, we know the current throughput by default. For resistors, we have Ohm's law that tells us, but for the voltage source, there's no unless we use the rest of the circuit to solve. There's no way to do that. All right, so let's jump into this example. And so instead of writing out that long title, I'm just going to say nodal analysis again, because this is really what we're doing, repeating different ways, different variations of these problems. Okay, so this is what our circuit looks like. We have a dependent current source, which is equal to 2,000 times this value Ix, whatever that is. We'll show in a second what it is. Okay. So, label everything. Node number 1, node number 2, node number 3. Step 2. Which node makes sense to choose as our reference? So even though this is a dependent voltage source, it's still, in terms of ranking difficulty, you want to go with any type of voltage source between reference and non-reference nodes over between two non-reference nodes. So that means we'll choose 3, right? All right. And we don't have a super node for this problem because the way we chose our reference. Okay, so let's define the number of nodes and then the linear algebraic structure. How are we going to, how are these going to look as matrices in the end? So first things first, the number of nodes here is 3. We know that. And so let's start off by writing the general form that how this would look, right? We have what we'll call I1 and I2, which in this case we will know I1 is equal to 0 because there's no independent current source flowing into node number 1. And then for node number 2, it's 4 milliamps, right? Normally, we would have a 2 by 2 admittance matrix, Y11, Y12, Y21, Y22. And then that would lead us to a value of V1 and V2, which is the same thing as V13, is the same thing as V23. Right? So this is going to be our original form. But there's a problem here. And the problem is the top equation, right, is based off of KCL. It's problematic because we can't define KCL for this node number 1 the way that it's set up, right? It just we don't know what the current is through it. So we're not going to be able to use this form.